So in general, we looked at the other Thursday. If we have a function e to the x, we looked at the kind of cool property that has as its derivative is also e to the x. I suppose the first question I would ask is, if it's not e to the x, if it's e to the anything else, so let's say any other function of x, so I'll put in any other function of x, so for instance 2x, would the derivative then be just e to the fx again? That's the question. What's your thoughts on this?
So isn't it, if it's like e to the 2x, it's just like e to the x times e to the x, so.
Okay, so y is e to the 2x, and you're saying that's the same as e to the x times e to the x, yeah?
Yeah.
Could I, well, if that's the case, then I can use product rule here, can't I? So the derivative would be the first by the derivative of the second plus the second by the derivative of the first, something like that. Yeah. So the first by the derivative of the second is going to be e to the x times e to the x, plus the second by the derivative of the first is e to the x times e to the x. So we're already seeing here that the derivative of this is not going to be just e to the 2x. It's going to be, well, that's e to the 2x here, but we've got two of them, don't we?
Yeah.
So that's 2e to the 2x's. Now, what is the derivative of 2x?
2.
2. Is that a coincidence?
No.
No, it's not. No, it's the chain rule. So what we're really, we can do this product rule, we can split it up and get many e to the x's, but perhaps when it gets a little bit trickier, that won't be as easy. Good morning, Badai.
That's just so I'm late. My Wi-Fi was acting really strange.
Okay, so the chain rule in general is when we split it up and introduce this u character, and then the du's will cancel. So in a way, we're doing e to the u times then 2x in a way for chain rule. So the derivative of e to u is just e to the u, and derivative of 2x is 2, and then the du's will cancel. We put back in e to the 2x times the derivative. Sorry, so that's it split up, not derived. That's it derived, and that's just 2e to the 2x. Now you don't have to remember it using the chain rule. We can just approach a problem straight away and know what the derivative is. So for instance, let's go with a relatively simple example. E to the, let's say our function is, I'm off screen, 1 second. Oh. E to the negative 2x squared. Okay, so if I have that as my function, what would be the derivative? Anyone jump to that straight away?
Is it negative 2 times that?
It's going to be more than that. So it'll be whatever this is times the derivative of the function. So we can break that down a little bit. So if you want to write it, it's e to the function as it was times by the function derived. And this is the function.
Minus 4x.
Okay, yeah, so yes, it would be. So what it originally was e to the minus 2x squared, and then we would times it by, well, what's 2x squared? Negative 2x squared derived, multiplied down by 2, we get minus 4x, and take away 1 from the power, which is minus 4x. And then you could tidy that up a little bit by putting that in front. Minus 4x times e to the minus 2x squared. So hopefully that clarifies any e to the x, or e to the, when x is a function up here.
Yep, thank you.
Okay. So quite often then they can show up an exponential in more difficult problems. So perhaps you saw that in the homework that we got. Let's pick one randomly from page 452. So I'm going to do question 4D. Not this yet. It's looking for y is 2 minus x e to the 3x on the bottom. And we're looking to find the gradient at x equals to 1.
I mean, you can rewrite that as like e to the 3x times negative, to the power of -1, right?
E to the negative 3x?
No. E to the power of 3x and then close parentheses to the power of -1.
Yeah, if I wanted, yeah.
Or you can wait. Could you also use like quotient rule instead of converting it to product?
Yes, it's quotient. So there's a number of ways you can split it up into its different components and deal with them both separately. And as you said, use e to the multiply up by a minus power, so it'll be e to the negative 3x. So we need to get the gradient function of this in order to evaluate the gradient at that point. We can evaluate this point, no problem. X is 1, we get a y point, but that's not what we want. That might be useful if we wanted to find the equation of the tangent, so you can get a point on the line. But we must get the derivative of this and then sub in x equals to 1. So we need to find out what that general function looks like. And yeah, so I'll use the quotient rule, I think, which is going to be the bottom times the derivative of the top. Are we happy with -1 here?
Yes.
Minus then the other way around. So 2 minus x times, okay, now what's the derivative of the bottom here?
Isn't it going to be 2e to the power of 3x?
You might see that as a 3.
3e to the 3x.
3.
Oh, 3, right.
Yeah.
Yes.
So the derivative of 3x is 3. All over, well, e to the 3x squared. All right, so we'll just tidy this up, and then we'll have to evaluate it at x equals to 1. So that's going to be just negative e to the 3x. This bit's a little bit more complicated. I'm going to say, well, let's multiply it. I've already noticed that there's a common factor between all these three, isn't there? And it might be a little bit easier if I were to remove that at this stage. But I'll come back to that. Perhaps I'll just multiply in and then remove it. So that's minus 6e to the 3x when I multiply it by the 2. I'm just absolutely making sure. I think that's plus x, or plus 3x, x times this, e to the 3x, all over e to the 3x. Now I'm going to write this like that, squared. Okay. Now, if all terms contain e to the 3x on top, and there's e to the 3x on the bottom, it's like all terms containing a 5, and there being 5 times 5 at the bottom. There's no point in multiplying all terms by 5 and then dividing them by 5. So I'm going to do this. Now, you didn't have to do this. You could have evaluated it. But I think that's easier if we divide in one of them. All right. So that's not disappeared. That's minus 1, isn't it? Minus 6 plus 3x all over e to the 3x. And that's my gradient function. So if I could make that minus 7, of course. I'll do that in a second. That's my gradient. So it'll give me all the gradients along it at any stage. But I just wanted at x equals 1. So I'm just going to sub in 1. So it's minus 1, minus 6, plus 3, all over e to the 3. So that's going to be minus 7. Minus 4 over e to the 3. Perhaps I can evaluate that using calculator. Depends on which paper it's in. You could also bring the e up if you wanted to. You can get a decimal value for that if you use your calculator. I'm not going to.
So are we supposed to know the properties of natural log functions, or is it okay if we can just graph them instead?
You would have to have a reasonable idea of it without a calculator, yeah.
I mean, yeah, I know how it looks like, but maybe if it was being translated to all different places, like, I'm not sure.
Translations not so much, but they would follow the general rules of translations, like subtracting and things like that. Subtracting a number. You can play around with it on Desmos and see what you would get.
All right.
But yeah, in general, you have to know the general shape and then any basic transformations. Yeah. Okay, let's look at the natural log function actually, since you brought it up. Why not? So, all calculus with some logs. Because it's nearly holidays. All right, so we have y is equal to ln x. Yay. Okay. Of course, could write that a different way using log base e to the x, couldn't I can also write this another way. If I wanted to rearrange it a bit, what would x equal if I wanted to rearrange it a small bit?
E to the y.
Yeah, e to the y, yeah. Should know that from our... I always like to use my test case here. I know that works. 2 cubed is always 8. If I wanted to rearrange it, and I can just apply that here if I wanted. If I couldn't have remembered, I always have this test one to go back to, because I know 2 to the power 3 is 8. All right. Now, I'm going to do something interesting, well, a bit different. I'm going to derive this with regards to y. I'm going to derive x with regards to y. So it's dx dy this time. What's the derivative of e to the y? Didn't hear that.
Just e to the y.
Yeah. It's just if you were to call the y-axis the x-axis and the x-axis the y-axis, if you want to think about it that way, it's the same thing. It's the exact same, just different variables. Same as e to the u, or any e to any one variable, a single variable, will be just derivative. So e to the x is e to the x, e to the u is e to the u, and e to the y is e to the y. All right. But that, of course, is not the derivative of this. That's the derivative of this. But this does look an awful lot like dy dx. So perhaps if I were to write it dy dx, what would it look like?
Of EY, sir?
Yeah, so dx dy is e to the y, and what's dy dx then if dx dy? So in other words, if a over b is something, what's b over a?
Would it be y over e? I mean, like e, like y to the power of e?
Nope.
Just 1 over e to the y.
Yeah, so if a over b is 1/3, what's b over a? It's 3 over 1.
Oh, yeah.
Yeah. So if dy over, or dx over dy is ey over 1, I suppose you could say, dy dx is e to the y. Now that still isn't my function, is it? No.
Yeah.
But what is e to the y? I defined it at the start. It is x. So the derivative is 1 over x. I defined that at the start. I just swapped them, but that's okay. I haven't broken any rules. I've just followed the rules of algebra and fractions, and did my calculus for e to the y, and it works out. So the general derivative, if we have y is the natural log of x, the general derivative is 1 over x, according to the work I've just done. Do you believe me? I'm not
Sure.
entirely, I'm not sure. Yeah, of course. Yeah. The teacher said it must be true. Kind of makes sense. It looks right. But does it make sense graphically? So, Badai, you know the shape of a logarithmic function. What's the shape of a logarithmic function? LNE.
It's kind of like a sideways quadratic, but only positive values.
Yeah, I suppose you can think about it that way. It's like this, isn't it?
Yeah.
Yep, only positive values, yeah. All right. What's 1 over? So that's ln x. What's the 1 over x?
Oh, it'll have another side. Like it's basically a rational function, right?
It is. Yes, it is basically a rational function. Yes.
Yeah.
Let's do this in another color, just so we see them. Oh, my kingdom for a highlighter. Yeah. Here we go. So this is 1 over x. Something like that. Of course, there's a bit to it over here, but my inputs, if I'm looking for the, if this is the gradient function of that, this is the gradient function of that, my inputs aren't going to go below 0, are they? So I don't really care about this side, but it would have its buddy over here. But I don't really care about that side because the inputs will never come to that. So does my derivative, my gradient function, match the gradients of the original function?
Yep, it's high, or the gradient's high, and then at one point it's the same, and then the rest is, yeah.
Yeah, I'm quite happy. I'm quite happy with the way it looks. If we think about the original function, it's quite steep here, isn't it? It's flying up steep here.
Really steep.
It's
If the
steep.
tangent's really steep,
Yeah.
that means the gradient function would have to be like high. So
Yeah.
I think it does make sense.
So yeah, so let's just pick this point here. Whatever the x value is there, it is forming a steep gradient. So therefore, its corresponding buddy here must be a high number because it's a very steep line. And it is. It's a high number. It's higher than here, which is a more shallow gradient. And of course, its buddy here is a smaller value for y. And what's happening? Well, the log function is flattening out, isn't it? The gradient's getting closer and closer to 0. It doesn't quite flatten out, but it's getting pretty close. And so this 1 over x is doing the right thing then. It is getting closer and closer to 0, so showing that this gradient is flatter and flatter, but it's not quite going to reach there, is it? It's going to tend towards it, asymptote, yes, of course, but not quite get there. So this makes sense graphically, and it makes sense using algebra and calculus. So I'm confident of saying that this is a concrete rule. So the derivative of a log to the base e is 1 over x. Great. Now, talk to me about what would happen if that is not just to x. And that's perhaps the difficulty. So we can say in general if it's ln x, but what happens if it's ln? What happens if y is some function then? So in other words, 2x. Is it always 1 over? Well, I think we'll switch to Desmos and have a little look. Okay, so whoa. Apologies if you're on earphones. Okay, so let's present. There you go. Okay, so we're looking at next. Oh, look at that! I've already written it in. So ln x, and this will give me the derivative straight away if I just click this button. Okay, so hopefully you can see that. Yep, that matches what we drew. That's cool. Now, I'm not happy with that as a general rule, so I'm going to do 2. Okay. What happened that? Remember, this was our original function. 1 over x. I have it in here, perhaps. I'll look at this for a second, just so we can see. That was the derivative. Now, that's 1 over x. Ignore this bit over here. That's what the derivative of ln x is. This is ln 2x. What's the derivative of ln 2x then? So I get rid of the function. Is it the same? It looks like the same. Yeah, they look like they're overlapping. Okay, maybe I haven't made just a big enough difference to notice the difference. Okay, so let's perhaps make this 200. Oh, that's definitely different. Or is it different? Oh, no, it's not different. The original function is different, but if it's just some multiple of x, it seems that the gradient function stays the same. Okay, but what would you like me to test next? So just there.
Thing.
Yeah, you've got squared or squared. What did you say? Squared, yeah.
Yep.
Okay, let's have. Oh, something's gone out. Oh, that's gone all over the place. So this is my original function now. Log of x squared is this weird thing. So you can get negative values, of course, for x because x is going to be squared. What does the gradient function look like? Kind of still looks like
Same.
1 over x. Is it the exact same? No, it's not. Something's happened. What translation has happened for 1 over x? 1 over x, have we moved somewhere? Something's happened to 1 over x. Is it then 1 over 2x? No, that's not right. Is it then, so I'm thinking the derivative of this would have a 2 in it. So that's what I'm looking at here. I'm going to play with it. 2. Oh, hold on.
Yeah.
I put 2 up here. That's done something. That is, I think that's matched it, hasn't it? That's gone and replaced it. It's the same one. Replacing it. That's gone. It's gone. Okay, so the derivative of this seems to be 2 over x. All right, let's make it more complicated. Let's put it, let's do 3 and just confirm that if I put a 3 here, it'll be the same. So there's my other one. That's what I hope it looks like. I'm going to replace this with 3 and it lands on it perfectly. Now, these are, yeah, these are working so far. Anyone want me to do anything else here?
Would the coefficient of ln affect it at all for the derivative?
So you want me to put 2 in front here?
That's just
Yeah,
like another x from it.
Oh yeah, it is.
Does affect it, doesn't it?
Yeah, so it's gonna be.
Yeah, it affects it.
But
What
then
about if it's more
like-
than just x cubed? I want to put in a full another function here, plus 2x. So that's the derivative. Is that matching? No, it doesn't match anymore. Doesn't match anymore. So I need some sort of rule here for me to.
Well, it's 3. It's definitely still 3. It's just 3 plus something else, I think.
Yeah.
Okay, so give me a suggestion that will match this up. 3
It can't be an integer.
plus can't be an integer, so 3 plus x.
No, that just moved
Let's
it.
do the derivative of what's inside that ln. So would it be like
3x squared?
squared plus 2? Oh,
No. No, that's not working for me. Maybe if I put the original down here, because remember it was over 1 over x I was looking at, and it was 2x, and so on. Maybe if I put the cubed plus 2x down here.
that works.
Oh, I'm so surprised. That worked. Okay, so that's an overlap. So what am I seeing here? How did I develop this function? Well, it's 1 over the function, isn't it? 1 over whatever the function was, ln, and that follows the kind of lnu, the chain rule type thing, doesn't it? But then if you use the chain rule, you also need the derivative of the inner part. And that's what you need to multiply it by. So this is a chain rule. It's 1 over u, which is this, multiplied by the derivative of u, which is 3x squared plus 2. Now, perhaps we can just change this ever so slightly and just confirm our work. Let's do just 5x. So I would have to adjust this, wouldn't I? The top of this function would have to change to the derivative, and the bottom of the function
plus 5 on the numerator.
the numerator you want 4x, is it?
Yeah,
Plus
4x.
5.
4x plus 5.
Yeah, let's get down here. 4x plus 5. Okay, that's not quite right, but we need to fix the top first.
No, isn't the top 4x plus 5?
Oh, I thought you said the bottom. So this is 2x squared
Yeah, the bottom remains a
plus 5x.
parent function.
And the top then you're saying is the derivative. So 4x plus, hold on, there's 4x. Is adding 5 going to move that derivative, this line, to the right 5?
No, it's gonna move to the left, isn't it?
You said 4x plus 5?
Yeah.
Is that matching our derivative? What's the derivative? Let's get rid of that for a second. According to Desmos, the derivative of this function is this thing. Now, what we have done is, we've created, oh, hold on.
We got an extra.
The only bit that doesn't fit it is this bit.
Too big.
Why does that make sense?
Because on the, well, I mean, it looks like there's an vertical asymptote between like -2 and 0.
Why would there be, okay, yeah, so all graphs seem to have that asymptote, including our attempted derivative. That's an asymptote here at, it's probably at -2 point something, isn't it?
Yeah.
And definitely an asymptote here at, looks like 0. What would be a condition that would make an asymptote?
Something that x, like a value for x that makes the graph undefined.
Yeah, so let's think about our original function here without the derivative. It doesn't have any values between here and here. Okay, let's pick a value. -1 is an easy one. Let's pick a value. -1. 2 times -1 squared is 2. Oh, that's going to be -5 now. It's going to be the natural log of -3. What's wrong with that?
It's like getting a negative exponent.
Yeah, it's given ln e to the -3. Is that illegal? Is that defined? Can we get an answer for that?
No, not
We cannot. We can, if our x, if whatever we get from here is a negative answer, it won't work for the original. So therefore, when the Desmos, does the derivative function, it allows for that, doesn't it? It allows. It says, well, there's nothing here because the original function has nothing there. So the gradient function won't have anything there either, because between here and here is undefined. Now, when we independently did this graph, which had no relation to our first two graphs, there's no problem with this. This is the answer. It's just the fact that we didn't relate it to this. It is correct.
So in our answer, if we write that, do we just set up a domain or something?
Yeah, you can restrict the domain, but generally it is the it is the gradient function. You may be asked to you would be asked to use it, or asked to find a place perhaps where it doesn't work, and that's where you would restrict the domain. If you were just asked for the gradient function, giving that should be fine, but you should then realize perhaps if it's logs or the square root of negative numbers and stuff like that, just check for the domain. There may be a barrier to it, but it depends on the individual question where they ask. Most of the ones in the book that you're going to be looking at is just going to be, give me the derivative, and perhaps use the derivative to find the gradient, which you should be fine with. Okay, I'm going to go back to my screen. All right. Did it again. All right. So, if there is a function then in it, and this is what we saw, the derivative would be, give me a general rule here, what would dy dx be?
Of ln of x.
Anyone have the die? You've got a general rule?
For logarithmic functions. Hello, can you hear me?
Oh, I've turned off the sound.
Just say the like f dashed of x over f of x or something.
Yep. The derivative of where the function is over whatever the function is. And that's...
But this only applies to logarithmic functions, right?
What do you think?
I suppose so. I mean, I haven't come across.
Give me an example of another function. Any other function besides logarithm?
1 over x cubed.
Okay. So if y is 1 over x cubed, we know how to deal with this, don't we? Because that's y is equal to x to the minus 3. This is just by rule. So, to answer your question, yes, of course. Yeah. Yeah. So this is something that if you saw in a question before today, you would go, don't know. This is something, every other function that you've come across, perhaps you've gone, I have a good idea. Perhaps I use the by rule, which is this. Perhaps I use the product rule. Perhaps I use the quotient rule. Okay, now I know how to do e to the x. So maybe I use the product rule and the e to the x rule. Now this is an additional rule, which they can throw in any old question. Let's have a little look at an interesting use of this. So I'm moving on. If you're in the book, following on the book, I'll do something on page 455, perhaps. Maybe I'll do 456. So this is from page 456. If you're rewatching this, I'm going to do part 5D. I haven't done this already, but it looks horrible. And x cubed over x plus 4 x minus 1. All right, and that looked like a mess. If you guys can try and do this quicker than me, go for it. If you want to just follow, go for that too. I'm just going to pause for a second so you can get a head start. Take it down. Okay, hopefully you guys are working away frantically. For this, I would need fx. For this, this is fx, of course, but I'm going to just call this, perhaps I shouldn't do that. fu if you want, but we won't do that. I'm going to start off with doing 1 over this. X cubed over x plus 4, x minus 1. 1 over, okay, it's a mess, but we'll have a look at it in a second. And that's going to be, I don't want 1 over, I want, of course, well, I can times it by the derivative. So I'm going to come back to that. So f dash x if I want. Of course, when I say f dash x, I do not refer to this function derived, I mean the inside function. I just use the same terminology. And hopefully you're doing this faster than me. I'm just going to take out this function and just do a bit of rough work and get f dash x. And I'm looking at that, and I think that's a quotient. And it is. So I'm going to do the bottom times the derivative of the top. Okay. And I'm going to subtract the top times the derivative of the bottom. Now, there's a couple of ways I could approach the derivative of the bottom. It in itself is a product. So I could use product rule. Or I could use, I could simplify this in another sidebar. X plus 4, x minus 1. Well, simplify or expand, whichever terminology you want to use. That's x squared plus 3x minus 4. So the derivative of that, if that's y, dy dx, this one would be 2x plus 3. And that's the derivative of that. So I did another sidebar, and I'll put that in here. 2x plus 3. So that's v times u dash minus u times v dash. Okay, and I got v dash over here. This is the v dash section. Okay. All divided by v squared. Now that's this squared, or x plus 4 times x minus 1 squared. Wow, what a mess. This is the numerator of this. Okay, but it's a fraction over a fraction. So remember our fractions, a half divided by 3/4. How do I do this? Half divided by 3/4. It can be written a half divided by 3/4. And it'll be a half times then 4/3, the reciprocal. All right, so let's do the reciprocal. So I'm going to keep this fraction, the numerator fraction, which is this, the same. And I'm going to multiply it by the reciprocal of the denominator. So this is just testing my fractions work. So I'm going to write out my f dash x again. You probably wouldn't need to do this. Anyone finish this yet? Or are you just watching me? Let me do all the hard work. I'll take it from the silence that you're watching me. Multiplied now by the reciprocal of the denominator. So that's x plus 4 over x minus 1 over x cubed. My goodness. Well, first thing I notice that this is squared. So it's times it by itself. And there's one of these here. So that is going to cancel out with one of these. So the squared is going to go. That's convenient. Can I cancel this x cubed with this?
No, not yet.
I cannot. Because that x cubed affects this as well. I could perhaps do x squared. Couldn't I? Cancel x squared, so I'm just left with x here, because it goes into this, x times, and goes into that once. So it goes into both terms on top. I think I can do that. That's okay. I just don't want to multiply this out fully with all the messy stuff. So I'm just pre-canceling. Now, this has an x term. Now, this is going to have, I won't all have x terms because it's going to be 4 here at the end. No, I can't do anything else because I just saw that this multiplied, but I can't do anything else. Okay, so I'm going to tidy up. This can't cancel with this either for the same reason as this is not going to work. So perhaps I'll square this out. So I know what that is already. X squared plus 3x minus 4. That's times 3, so I don't want to rewrite this. I'm just going to do 3, 9, and 12. Yes, that's kind of cheating. Anyway, minus 2x squared minus, so I'm multiplying in here the x, minus 3x's. Do stop me if you see a mistake or want me to redo something. And that's just going to be x times the bottom here. X plus 4, x minus 1. All right, let's add any like terms. This is a 9x, and that's 12. I'm going to add any like terms I got here. Well, 2x squareds take away from the 3x squareds, giving me x squareds plus 6x, when I do the x's, minus 12, all over x times x plus 4, x minus 1. Now, that's what I think the derivative is, f dash x. Remember, this f dash x here was not f dash x. You could call it g, I suppose. Okay, so that was the derivative of this. Now, I'm not entirely sure. Very unconfident of my mathematics today. I'm going to check on Desmos. Okay, so let's look at Desmos again. Okay, so we're back to this old jazz. You can see what's coming next, can't you? Sine and cos. All right, so my derivative is a mess, but let's put it in. ln x cubed. That's divided by, I'm gonna, oh no, not like that. Divided by, and as it is, x plus 4 brackets minus 1. Okay. Be my, I don't need this anymore. So that's my original function, an absolute mess of a function. Its derivative, oh, it's also a mess. Have I got it correct in my previous screen? So I'm just going to edit this one. Let's see if we got it. If we didn't get it, well, we've obviously just made a calculation mistake. X squared plus 6x minus 12. Doesn't look like it yet. Let's get rid of that one for a second. Let me watch this. Okay. X times x plus 4 and x minus 1. All right, the moment of truth. Does it overlap? I'm not. Hey! Now there is a difference. The one I've drawn, let's move all the other ones. The one I've drawn is this one. Okay. When I overlap the derivative, you can't see it, but when I get rid of my one, you can see that this bit has gone. Any place, I think, beyond -4.
Wait, sir, can you click it again?
The original function or my one? Here's my one.
Like, yeah, that one, yeah. Oh,
Here's
okay.
my one. Here's the derivative. My one, derivative. So it's matching,
come-
except.
Why does it do that?
Yeah, you tell me.
Well, at 4 it can't hit because then you'll get an undefined, which is an asymptote.
Okay, so at 4 is undefined. Why?
Right.
Why does like -5, -6, -10 not work then?
Because I guess there's no, in the original graph, there's nothing there.
Okay, well, let's look at the original graph. Let's get rid of both these again. Here's my original graph. There's nothing beyond -4 because, of course, the numerator would take over the cubes. And, of course, a negative number cubed is still a negative number, isn't it? So the numerator is taking over this fraction. The -10 is going to be, -1,000 up here, and you're going to get a negative number because what's -10, for example? That'd be -6 times -11. So it'd be -1,000 over -6 times -11, which is +66. So it's a negative number, -1,000 over 66. And you can't get the natural log of a negative number. Try it if you want. Ln. So y equals, this is a new one, ln, do just a. Look at our sliders just to make sure that we can't get, it's not telling me I can't put in a slider. Where's my slider? I defined a somewhere else. Well, let's just do it manually. So 3 is fine. -3, undefined. Okay, so you can't do a negative number. So when this spits out a negative number, this bit of the function, it's undefined. So that's why my original doesn't go beyond -4. That's why their derivative doesn't go on beyond -4, but our derivative does because we haven't linked it to this. It's just a normal rational function. It's fine that we get negative answers. There's no problem for it, but when we link the two, it doesn't matter. Okay, so hopefully that does make sense. Okay, let's continue on this screen. Back we go.
Sir, I just have a quick question.
Yes.
Going back to the question, the previous one.
This one, yeah.
Yeah. On the right hand side. How did you get x plus 4 times x minus 1 again? On the right hand side.
Here?
Yeah.
So that was our denominator. That is the function.
Right.
So 1 over 8, or sorry, the derivative over 8 is where we started. This is it as the denominator.
Yeah.
Because we know the rule from the previous page. It is, if we have ln a function, it is the function becomes the denominator, and then we have to get the derivative of the function.
Right. Is that in our formula booklet or not?
Is it in your formula booklet? I think it would be. It wouldn't be written. The only thing that would be written in your formula booklet, I think, is this. That's written in your formula booklet, but this would not be, because this is just using chain rule. This is written because ln u is 1 over u, and using chain rule we can prove this, or you should be able to do that. So this is in the formula booklet. This is not. So if you want, you can remember it.
Okay.
But yeah. Okay, so that's this. So I finished it off by just using reciprocal of fractions. All right, now we must do trigonometry. I've been avoiding it, but we will get there. So we do have some presumed knowledge entering this course that you do know trigonometry in some form. So let's discuss what we know and see if we apply it. Now, Rigel, you were asking about this in the last chapter 16.
Yeah.
Sin x over x equal 1 or whatever, the limit equal 1. Yeah, and a very legitimate question. I kind of skipped over it because we weren't ready for it. We're probably still not ready for it, but I will talk about it now. Okay, so we're going to look at trig functions. We're going to look at the derivative of trig functions. We're going to look at it in simple terms first by graphing, and then we'll look at it in proving. So, Rigel, you were looking at the proof. It's going to be easier when we look at the graph. So the sine function, if we're dealing in radians here. So let's stop for a second. Radians. 90 degrees in radians? Does anyone know?
Is it 1/4 pi?
Anyone have a different answer? Is everybody happy with 1/4 of pi?
I think that's true.
You think it's true? Okay.
Yeah, it is. It is.
Okay. We'll be coming. Hopefully, you're familiar with something called the unit circle. So we know 90 degrees is here, 180 degrees is here, 270 degrees is here, and we go back to 0 or 360 if you want to do your full revolution. All right. So if we have a unit circle of distance 1, talk to me about the circumference of that circle. So the radius here is 1, or equals 1. Circumference.
2 pi.
So the distance, so how do we get 2 pi? Well, that's a formula, and it's 2 pi or, if you want to use the formula, or pi times the diameter. The diameter of this would be 2, wouldn't it? Pi in itself is an amazing number. That every circle in the world attests to pi, doesn't it? It's a ratio, it's a perfect ratio. Because we got a diameter of any circle in the world, and if you multiply that diameter by 3.14159, etc., if I multiply that, I will get its circumference. Sorry, the diameter should have gone through that. No matter what the circle, the earth, coin, the bottom of this Tabasco bottle. That's kind of cool. All right, so it's just pi times the diameter. Now, that's nature's number. It's a bit like when we dealt with E. We looked at E and its principle coming from compound interest, just compounding time. But anyway, back to this. Is this unfocused for you? It's unfocused for me. Okay, so we'll come back to this then. So Rigel, you've said that 90 degrees then is pi divided by 4. So
you'd like a lot.
Change your answer. What is it? So the distance, so we just said the distance around this unit circle is 2 pi. All right, just go. The distance around this unit circle is 2 pi. So what's the distance half the circle?
Pi?
Yeah, it'd be pi, yeah. Okay, the full distance is 2 pi. So what's half the distance from 0 to pi? will be here.
Well, so would that be? Yeah.
Be pi halved, pi over 2.
Right.
Is that the same as the angle 90 degrees, pi over 2?
What do you mean if it's the same?
As in, like, can I say that 90 degrees is pi over 2?
I don't think so.
Is this distance directly related to the angle it's making?
Yeah.
Yeah, it is. However far you go, it's directly related to the angle it's making here.
Oh yeah, it is. Yeah.
Yeah. So when we traveled this far, pi, it's 180 degrees. I know that. So if I travel half that, pi over 2, it's 90 degrees. And it works for all angles along this unit circle. So that's one way of working out radians. So we know 90 degrees is pi over 2. That's something we know. We also know 180 degrees is, let me out here.
Pi.
Pi, thank you. 270 degrees then would be?
3 halves pi.
3 halves pi, or 3 pi 2. And 360 degrees is then just 2 pi, which we figured out. I can go further than that, of course, and we will be going further than that. We do trigonometry, and you hopefully have gone further than that as well when you did trigonometry. Perhaps you forget, but that's okay. So let's look at this again. I'm going to just take a right angle triangle out of this just to look at it. This is the unit circle, yeah? So this is a right angle triangle from the unit circle. This is this triangle, just I made it a little bit bigger. That's theta, still an unknown angle, but we know theta is directly related to the distance around the outside, isn't it? So the further you go on this circle, the bigger theta is going to be. Yeah. All right. So when theta is flat, so it's a flat. I've squashed theta so much that it's flat. What's this length when theta is flat? So in other words, when the angle is 0.
What, the adjacent side?
The adjacent side? Yeah, you could talk about it as the adjacent side, yeah.
The perspective of theta.
Want to know the length of it?
Radius?
Yeah, it's radius length. What's the radius length of the unit circle?
1.
Thank you. So if that's 1, everywhere along it is the radius length. So that's 1. So when theta is 0, when the angle is 0, that length is 1 here to here, yeah? But of course, it doesn't work like that anymore when you start to increase that angle. But we know that this length is 1, isn't it?
Yeah.
Okay. Right. And this is where your adjacent and hypotenuse and all that comes in. So this side you would call opposite, I suppose, when you did trigonometry. This side would be adjacent, as Dustin said, or but I can't remember. Right. So so in general, so you're going to your classic sine ratio, cos ratio, tan ratio, which perhaps you learned off by heart. Silly old Harry and all that, Sokotoa or whatever you did. Let's talk about that for a second. Sine, cos, and tan. Let's just draw more triangles. So I'm going to pause that for a second. Come back, looking at why sine, cos, and tan work. Let's think about tan. It's probably the easiest one to show a representation of. Okay, so I've drawn 3 triangles. Now, perhaps not, but hopefully these lengths kind of all look the same. The hypotenuse length looks kind of the same. What I've done is I changed the opposite length and the adjacent lengths. Yep. All right, this is triangle 1, 2, 3. This one I've tried to draw an isosceles triangle, so that's the same length, that's the same length. Come back to that in a second. Which has the biggest angle?
1.
1. Is that directly related to the opposite side? The length of the opposite side?
Yeah.
Just the opposite side?
No, I mean the adjacent and opposite.
Yes, the adjacent and opposite combined that would determine the length of that. But if the opposite is of a greater ratio than the adjacent, it's a bigger angle. So for instance, if I just thought about, I want to make a large angle, I would think about the opposite side, let's make it 10 centimeters. And I'm going to say the adjacent side, let's make it 1 centimeters. So the ratio is 10 to 1. That'd be quite a large angle. So 10 centimeters be there, 1 centimeters here. And I've already noticed that it's a right angle triangle, and that is a really large theta. Yeah? All right. So clearly, if I make the opposite ratio, the opposite over the adjacent as a ratio, so this ratio is 10 over 1, which is just 10. If I do the opposite, 1 over 10 ratio, I can pretty much say that that's going to be a tiny angle. And I can, of course, because if the length of the adjacent side is 10 and the opposite is 1, well, that's a shockingly small angle. So the ratio of opposite and adjacent affects the size of the angle. So hopefully you've done this before, and this is obviously just repeating what you learned in year 9 and 10 or whatever. All right. Okay, so that makes sense so far. So we can use the relationship between the opposite and adjacent to find the angle side. Now, what happens if it's an isosceles triangle? Kind of already know the angle. What's the angle size? If this is isosceles, because this is 90. This would have to be
45.
It's going to be 45 degrees, yeah. So what's the ratio? What's tan 45 degrees then? What's the ratio of opposite over adjacent? Well, if an isosceles triangle has the same length here and here, so for example, if I use 3, it's 3, yeah, it'd be 3 over
It'll
3,
be
or
1.
2 over 2, or 1 over 1. You can test that with a calculator. The tan of 45 degrees is 1. I don't even have to write it as a fraction. Okay. Now, in my unit circle, we know something special about, it's not tan 45 is 1, to meet the circle up. We know something special about one of the lengths only. So we have this length is 1, which is what I drew in the other picture. I know theta here. Now, the same thing applies for sine and cos. If you restrict the length of one of the sides and just play it around with the opposite versus hypotenuse, so imagine we restricted the length of the adjacent side here and just played with the opposite and restricted the hypotenuse. The larger this opposite side is, sorry, the hypotenuse would change as well. The larger this opposite side is, the larger the angle. The smaller this opposite side is, the smaller the angle. Are you happy with that? Even if the adjacent doesn't change length.
This is assuming that the angle is not 90 degrees, not theta, where it looks like it's 90 degrees.
This is 90 degrees.
Well, then if one is the hypotenuse and the adjacent is fixed, then there's only one like height.
Wouldn't be adjacent. Adjacent. The hypotenuse. The adjacent is fixed, but the hypotenuse is not fixed. Isn't that what I said? I did call it for that. The hypotenuse wouldn't be fixed, so the adjacent length is fixed. But once again, if the larger the opposite side is in ratio to the hypotenuse, the larger the angle. What I'm trying to show is that this opposite side, the bigger it is, if the adjacent is just the same length, the bigger the angle. Now the adjacent would come in if this was fixed at 1, of course, the larger the opposite is, the adjacent would have to come in a bit, wouldn't it? And that would still be 1. The adjacent would come in as the opposite. I'm off screen. The adjacent would get shorter and shorter if you wanted to maintain that as 1. Okay, and that's what happens as this thing goes around the circle. What you see is that the opposite side increases in size, but the adjacent side would shrink in size. So for instance, just use this as another, if I move that angle up here, that length has to be 1 because it's tracing a circle around. That has a really large opposite side, but a small adjacent side. Yeah. Okay, so let's just think about what I can call this side of that triangle in general and this side of that triangle in general, because the hypotenuse is always 1. So talk about sine then. Sine is the ratio of the opposite to hypotenuse, yeah? All right. So what's sine theta in this case? It's the opposite, which we don't know,
Just the opposite.
divided by 1, which is just the opposite. So therefore, we can say that all along the unit circle that this is not the opposite, it's just whatever sine theta is. Because it's just the opposite divided by 1. So that means just simple algebra, sine theta is the opposite. Because this is always 1, it's always divided by 1. And the same thing works for cos theta. So this length will always be the cos value of theta. Now what you should notice is perhaps that these work in opposition. As the sine of the angle gets bigger, the cos of the angle gets smaller. And that you can see that here. So if you get a really small cos ratio, that's going to be a large angle. If you get a really small sine ratio, that's going to be a small angle. So cos works conversely, it's called. All right, so as this traces around, we can see that sine over cos, sine is the this side of it, and cos is this side of it for all right angle triangles. Along it. What does happen when it goes straight up?
I guess the opposite and is 1 again.
Yeah, so the opposite is 1, and the hypotenuse is 1, I suppose, and the adjacent is 0, so it's just a straight line up. In other words, I can say that's 90 degrees. I can say that the sine of 90 degrees is 1. Yeah? So as it goes around and around, it's going closer and closer and closer to 1, and when it hits 90 degrees, it is 1. And then when it goes away, when it hits 180, what's the sine? So it's flattened down. It's a flat triangle. It doesn't. There's no sine. There's no up for it. Sine is 0. And when it continues on, what's the sine at this point? So it goes round and round and round and round. What's the sine? What's this distance? In other words, you can look at it.
1.
Yeah, the distance is 1, and it's down here, so it's -1. And when it comes back up here, it's 0. Now we know these now in radians, so that's pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so as it traces itself around. Now I'm going to plot that. Plot that motion that it's doing. And surely, as it continues on, as pi continues on, maybe when we get around to 360, 450 degrees, when we get around to here, sine hits 1 again. And we get around to here, which is going to be 540 degrees, sine hits 0, and we go around. So it's got this circular motion, which when we graph it on a Cartesian plane, where input output, it forms, so as these angles get bigger, we can graph it this way. So we can do pi over 2 as the angle gets bigger, pi, 3 pi over 4, or 3 pi over 2, 2 pi. We can continue on. So if it went on one more pi over 2, it's going to be, I think it's 5 pi over 2, isn't it? 5, adding another pi over 2. And you could go back if you want, minus pi over 2, because of course you can go backwards as well. If you go back 90 degrees, what's the value here of sine? That's minus 1. So we're just looking at that sine height here. What's that going to be? So it's, right, so let's plot that. When sine is 90, it's at 1. So it just goes from 1 to minus 1 on this graph. Sine 90 was at 1. Sine 180 was at 0, if you remember that. Sine 270 was at minus 1. Sine 360 is at 0. The next one then, after 360, is we trace this around 360. Remember, 450 is here up at 1. So that's 3 pi over 2. Okay, and it could go on. I think the next one's at 0. Working backwards, what's the sine at 0? It's just a flat line here. So it's at, well, it's at 0. So it goes through 0. What's the sign when it's negative pi? So it's down here. So it's at negative 1. Okay, so negative pi over 2 negative 1. Okay, so this is how you would form, or you should have done this before, how you form the sine function. So it seems to follow this curve. And I think it just keeps repeating like this. So it's called periodic when it does this. It keeps, so you may have talked about the period of that function. The period is from how often it repeats. So every 2 pi, it looks like it repeats. This is the basic sine graph. It repeats every 2 pi. Now, what I want to talk about next is its derivative. Its slopes. Now, I've drawn 2 definite places where I know the slope of that line is 0. What 2 places are they at?
The like maximum, minimum, or something.
Yeah, the stationary points would be the slope 0, because if I drew a tangent there, it'd be flat, wouldn't it? So that means if I were to draw its derivative, I know something for sure. Its derivative at those 2 points are 0, so it goes through here and here. Its derivative function. Now, is that it? Is that all I can say? Is that all I got?
Well, considering that if this goes on forever, then there's going to be new maximum, minimum every other one. So then,
Yeah,
this,
so it's going to be back here.
Yep, and it'll
here.
go on forever.
Yeah, so it's going to cross at those points. Okay, let's just look at the slopes then. Let's just look at positive and negative slopes. So I think all from here to here, that's positive, all positive slopes. Just looking at the slopes of the tangents, yeah? And after that, this point, it's all downhill. Downhill, downhill, downhill is easing off, it gets to 0 again. Uphill, 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 uphill.
It's just going to be the cosine graph, isn't it?
Hey, where do you think the slope is steepest?
Yeah, right at where it hits the, or where the sine function hits the.
Here, so that would be the maximum. That looks like the steepest there. That's going to be another maximum. Yeah.
But sir, would the gradient function of cosine be sine?
Well, let's look at what this, we haven't even drawn this yet. So if I remember, this has to go through these points, the ones marked in yellow, and it has maximums at these points. It has to be above the x-axis between these 2 points, because it's all positive. So let's draw that. Reaches maximum there, comes down, goes through that point, reaches minimum, so it's the lowest, that'll be its steepest negative slope, then goes off again, has to go through that point, and then reaches a maximum here, and so on. Okay. So yes, this, the derivative, the gradient function for sine, is the cosine function. How do I know it's the cosine function? Well, if we remember at the very start, when theta was 0, what was this length here of the triangle? It was 1. So when there's no angle, cos, or the adjacent side, is 1 in length, the same as the hypotenuse. What's the cos value when it's 0? 1. After that, we noticed, or hopefully we noticed, as this traced around the circle, the adjacent side would get smaller and smaller and smaller until we hit 90. Smaller and smaller and smaller until you hit 90. And then, what happens? Well, the adjacent side starts, so what's the adjacent side then? Well, this is where you talk about reference angles and stuff. It starts to recover a little bit and get towards, when we get to here, it once again is at 1. It's a maximum here at 1, because that length there is 1, but it's minus 1. And of course that matches here. And then we'll have to discuss this further when we do trigonometry, but you can see that it does match the cosine function. And yes, if you were to do that from cos to sine, perhaps it does match. Now, I'd hope to get to the proof of this. I don't think I will, so I might as well make sure it matches by switching to Desmos to finish. All right. So let's go back to Desmos, our old friend. All right, so let's get rid of all that complication. Let's just do sine. Beautiful. 0. Oh, this is not in the scale we were looking at. Oh no. 1,
So
2,
you have to
3.
take out. You have to take out all the integer functions.
I should take out all the integer functions.
I believe so, because when I graphed wave functions on Desmos, it gave me the pi values. So you have to you have to x all the x plus 4, x minus 1, and then the third one as well.
So what it'll do is it'll give you the actual length of that circle. So think about it. If we had a circle here, not in this graph, but in general, circle, unit circle, it would trace around, and pi times the diameter would be a full rotation around the circle. So, so what's pi times the diameter? Well, the diameter is 2, unit circle, times pi. So pi is 3.14. So 2 times 3.14 is about 6.28, isn't it? And look. What's that? Oh, it even says it. But before, you can trace some points along. You can see that it's approaching 6.28, and that does reach 6.28. So this traces this scale is just the distance that it travels. Anyway, does the derivative? So I need to delete these now and call them f of x. Oh, I didn't mean to do that. So let's call fx equals sine. Okay. Let's get the derivative of that. So my functions, derivative, and I get the derivative of fx. Oh, like that. All right, cool. So the derivative is the sine. Is that the same as the cos function? Yeah. Okay, that overlaps. Cool. So I didn't Get rid of that, and the cos function's there. All right, so obviously the question is the cos function then, is its derivative the sine function? So let's look at the sine function before I find the derivative again. So there's the sine function. So when I click this button, I'm expecting to see match. Oh, it's not matched. So there's the cos function. That's the cos function. Here's the sine function. The derivative of the cos function is not the sine function.
But it's wait, so it's kind of basically 1 unit transferred to the left or right of the
Well,
sine.
let's look at the two of them. Okay, let's get rid of cos and let's compare. Oh, this is the derivative of cos, and this is the derivative of sine. Sorry, this is just sine. The one in black is just sine normally, and this is the derivative of cos.
Could you say it's just horizontally translated by 1 unit?
Not translated, is it? Well, it could. Yeah, I suppose it's translated not by 1 unit. It's translated by.
Oh, two, not 1.
Pi.
2.
Well, I imagine that it's.
In this case, it's translated by pi.
Yeah, it's translated by pi, but I think it's.
Flipped over the x-axis.
I think it's flipped. It's nice. It's flipped.
Yep.
So if I put a minus in front of it, it flips it over the axis, and the derivative of cos is negative sine. And that should make sense. Let's look at our slopes again. Okay, I'll let you go after this. Let's look at the slopes again here. The slope here is all negative. From 0 to pi is all negative. All negative. Now, if we just look at the normal sine function, what's the slopes from 0 to pi? They're all positive. All positive, the exact opposite of what we want. And we can fix that then by doing that. And that matches. So this black line is the slopes of this line. And we see at this point, from here to here, the slopes are positive, which means from here to here, they're above the y-axis, so they're positive. So hopefully that makes sense to you. The derivative of cos is negative sine. And we look at the proof of that tomorrow, I think, using first principles, which is more complicated. Because you need sine h over h. That's a bit messy. But I don't want to keep you from your other class. So I'm not going to set homework today. Let's just stop recording. Not going to set homework today. I would like you to delve into that a bit more. Delve into that a bit more. So we've pretty much done from the book up to 17H, up to 17H, so up to page 461. So you can go through that. We're going to look at inverse trig functions then. But we're kind of going to stick with trig tomorrow, and we'll see how much we get through. I don't know if we're going to get to inverse trig functions tomorrow, but we'll try and get as much done as we can. Yeah, so look at those questions from the book. Do try and do some questions if you have time tonight. You should spend at least half an hour doing some questions from page 454 on to page 451 or 461. So look at those. Do try stuff because I